The second most interesting thing is I modeled the problem a little bit differently. So this is what I say is, of course, my goal. I say that going from here to here, it has a reward of plus 0.001. So instead of minus, it's plus. And going from here to here has a reward of plus 0.001. I want the problem this way, so I like. So when you walk, you also reduce your tummy and you become fitter. So walking is good. Both of them have a positive reward. And I say that let there be absolutely no collision, so completely deterministic world. And if you model it like this, the result of any algorithm will, no marks for guessing, will turn out to be like this. So I'll go with the policy first. The policy is never reach the goal. Why? Goal will give you a plus 10,000, but who needs it? Become fitter, keep walking, and therefore the utility of here will be infinity, utility of this will absolutely be infinity. So if you give these problems to any algorithm, the algorithms will have to calculate a plus infinity, and because they have to calculate a plus infinity, we do know that all the computer systems have problems with infinity. More correctly, we will make an iterative algorithms that guess something and they keep on improving the estimates. And the moment your actual output is infinity, so you keep on improving the estimates, how much do you need to reach infinity? And that's bad. So for this, we will have another concept added, and the another concept added will be called as a discount. So you say that the immediate rewards are more valuable than the future one, or the future rewards are discounted by a factor of gamma, where gamma is, of course, the discount factor, and gamma is greater than 0 and less than 1. The tipping point is when you reach it at 1. So that's like saying it has a social analogy. I say I give you 1,000 rupees, I'm not going to give that to you right now or 5 days back, and all your interests are taken care of. So if you would have kept that 1,000 into your bank account, whatever your bank would have given you interest, I give you the same. And I ask you which one is preferable. Now is preferable. Who's seen tomorrow? Now is preferable. You want to become famous now or after 10 days? Now it's preferable. Now is always preferable. I give you a chocolate today or after 5 days. Now is preferable. So everything kept aside, now is more dear, now is more preferable. So we say future is not that important as now. So you say that the same reward, if it comes immediately, is important. Tomorrow, if it comes, it's also important, but it's not that important. It's slightly lesser than that important. And because we have changed that, so we will have to travel all the way back and do the discounting. So now I defined the total summation of all, and I add the term over here, discounted rewards. So similarly, I go around in this sequence and calculate what will be my total indicative utility. So let's do it. I'll not give you the expression. So I say my indicative utility is equal to Immediate is the most important. A little future is slightly less important. So that's number one, that's number two. More into the future is slightly more less important. More into the future is slightly lesser important. More into the future is slightly lesser important. More into the future is slightly lesser important. More into the future is, oops, I forgot, 0.1, 0.1, 100, 0.1, 0.1, 100, so this has to be 100, and 1000. Discounting. Future ones are slightly less important, where for this thing you can take gamma as 0.9. So you'll get almost the same number, which is 1799.6 that we calculated here. But you will see that it will get little reduced, just to say that future is little less important. So I'll discount off the futures a little bit, and that's intuitive. So do you want the 0.1 right now, or do you want it a little later? If it's right now, it's important. Later, it's 90% of the same importance. Do you want the minus 100 right now or later? Minus 100, immediately it's important. A little later, it is 0.9 into 0.9, 0.81 times important. This is 0.9 cube times important. Okay, there has to be a cube. Now let's see if we've solved this infinite problem. And of course, I will have to add discount everywhere. So it's in this analogy over here where we said that I get RSA S dash, and the future I only get gamma times US dash. So I get US dash and I discount it by a gamma. So I discount it by a gamma. I discount it by a gamma. I discount it by a gamma. So that's my actual expressions. And so to say that we really solved this problem, so let's try to see this. The policy is obvious, it remains as it is. Do we still get infinite? So I say Rmax is the maximum utility that is always possible, or RSA S dash is always less than equal to Rmax. So what's the maximum? You take infinite steps. What's the maximum reward that you can get? So you get Rmax immediate plus something which is less than gamma times Rmax plus something which is less than gamma squared times Rmax plus something which is less than gamma cubed times Rmax, and plus, so these are infinite terms, and this of course is equal to, so utility of S has to be strictly less than that. This is the maximum that you can get by accounting for the maximum reward of all times. So this is finite for gamma less than 1. Equal to 1, there is no discounting. So infinity is one reason for which we apply in a discount. There's another reason because of which we apply a discount. So for that reason, let's do something annoying. And let's say, what is the worst value of gamma possible? Gamma is equal to 0. So I say, what if gamma is equal to 0? So if I do that, I will get US is equal to max over A P of S dash given SA RSA S dash plus 0. As simple as that. And you see, is it a recursive formulation? Is it something difficult to solve? No, I know all the probabilities, I know the model, I also know all the rewards. And hence, this is nothing but a paradigm that you have already studied called as greedy agent or greedy programming. So an agent only tries to maximize its immediate reward, which is some of you students out there. Assignment, we look at it later. Utility can be positive if gamma is equal to 1. We don't care. Right now I'm enjoying eating a lot of chocolates. Right now I'm enjoying. You'll get fat. Utility for gamma is equal to 1 is negative. I don't care. Let me enjoy right now. Greedy agents always do whatever it pleases you. Somebody says 2 weeks before the exam, start studying. Utility is positive for gamma is equal to 1. I don't care. Let me watch another movie. It's giving me a lot of fun. At the last moment, then you start studying. Then you get reward. Then you get pleasure in studying because it's time of the examination. You study, you write down, you get things which are positive. So some of you are completely greedy agents, always doing things which maximize your reward. And therefore, I say let's study what is discount. So one extreme is gamma is equal to 0. You've got agent which is completely greedy. At the other extreme, you have gamma is equal to 1. The agent, it has a lot of respect for the future. So it treats future as important as current time. Now, this will take so this needs no computation, no learning. So that's easy to compute. And this will take the maximum time. You'll have to solve a lot of equations. We'll see how iterative they'll slowly improve. So this will take a lot of time to improve. And therefore, what gamma really also does is sometimes your algorithms may take too long. When they take too long, you reduce its time by setting a smaller gamma, slightly smaller gamma. Now, there's a visualization which you can do. This guy never saw the future and therefore took no time. This guy sees infinite future. This guy sees infinite future. Now, what happens is that if you have a sufficiently small gamma, let's say gamma is equal to 0.8. So what happens after time t? Future rewards are or let's say total rewards are, so I haven't written that equation, so let me write down. So what's the total reward that I get? Reward that I get in time 0 plus gamma reward that I get at time 1 plus gamma square reward that I get at time 2 plus gamma q reward that I get after time 3, 4 reward that I get at time 4 plus so on. Now what happens if gamma is equal to 0.8 after some time t? So after some time d, 0.8 raised to power t almost becomes equal to 0 even for r is equal to r max. So even if you get the jackpot highest reward, 0.8 raised to power t is so large that it's so small that it's nearly 0, or the future rewards are meaningless. And once that happens, what I have effectively done is that I've said that you only need to consider t times in the future, not beyond that. So this guy does not look at the future, this guy looks at infinite future, and this guy, it only looks at a sufficient future till time t. That's most of you agent. Have you decided what will you do after your retirement from your job? No. You don't look that much into the future. You only look one day, 1 month, 1 year, maybe a maximum of 4 years of undergraduation. Anything after that, you look at it later. So you have to watch this lecture because it has a positive utility, because you're looking at the time when you get your degree. You haven't done anything like retirement planning. So you're greedy in that long-term sense. You haven't looked that much into the future. Or with discount, what happens is that gamma raised party becomes so small that the agent only says that, look, I'll only look at t times ahead. I won't look at beyond that because the gamma raised party is absolutely so small. Now, a similar concept is also called as, in the AI terminology, a finite horizon. So you say that there's only a time t till which I look at, or an infinite horizon, where you say that I'll consider t is equal to infinity as well. Last things also I will have a look at, that's infinite horizon. Now we are still solving it at infinite horizon because even though it will become very small, it will still have in some value and it will have some kind of an effect. There are algorithms which specifically says that it's solved under finite horizon, which means we will consider everything till time t, and after time t we will not consider that up. Now the problem is, the moment you have a fixed time t and you will consider that up, you know, when I in the same grid search said you have 5 moves only, so you have sometimes to make suboptimal move, otherwise you won't get to the goal till 5 time steps. And these agents have exactly the same. You have exactly 5 moves, you have exactly 10 moves. Okay, I need to get the jackpot reward in 5 and 10 moves. So that time also becomes a factor, or we say that the policies are not stationary, they are also a function of how much time is left. We're still dealing with infinite horizon, or our policies are absolutely stationary. So the policy doesn't depend upon how much time is left. Coming up to and by the way, discount is the most famous technique of handling the problem that I just stated, infinite rewards, or you want to converge by some time. There are other techniques like ones which says that take the average reward instead of the total summation reward. So the average gives you a time till which after that taking more moves will become meaningless. So it again says that there's a time limit and beyond that time nothing will be considered. You're taking out the average, so sometimes it will not be useful enough. Those are complicated, they cannot be solved by the easy techniques that we are going to solve it right now. So discount is the easiest way to solve that problem about the infinite policy. So even if your utilities are infinite, your policy is never going to the goal. The thing which will happen is, for this problem, once you take the discount, this infinity will change as 0.001 divided by 1 minus gamma, and this will change as plus 0.001 divided by 1 minus gamma, where gamma is 0.9, 0.99, it's still finite.